Many of us wanted to turn a satellite TV dish into a concave mirror. Now we see how a mirror dish focuses the solar radiation, and it is obvious that this point will have a high temperature, which can set fire to wood, or blow something up, or melt metal, or for cooking.
Usually, a satellite dish is turned into a mirror through sticking small pieces of mirrors, or sticking reflective films, or some other way. Our concave mirrors appear to be very cheap, and therefore it seems to us that they are capable of producing cheap thermal energy and electricity. That is why we ask the question, can we install thousands or millions of our cheap mirror dishes which will give us a lot of cheap thermal energy and electricity, so that such solar power plants are better than thermal and nuclear power plants and solar panels? And the answer to this question will surprise you. Now I am showing the first option, which suggests that a mirror dish must focus solar radiation onto a similar Stirling engine. These are examples of the first option from various bloggers, when a Stirling engine converts the thermal energy into rotation of an electric generator. The second option suggests placing a small solar panel here, similar to how this mirror dish focuses solar radiation onto this photovoltaic panel, which is water-cooled. The third option is used by this Indian solar power plant, where the solar radiation from the mirror dishes is focused on these cast iron receivers and heats them to a temperature of about 400 degrees. The thermal energy turns water into steam, which moves through these pipes to this turbine with an electric generator. Unfortunately, those three options are not suitable for us, because our goal is victory over thermal and nuclear power plants, and therefore the cost of our solar electricity should be about 5 cents per kilowatt-hour. In addition, I remind you that we want our mirror dishes to be better than solar panels. That is why we must pay attention to the fourth option, which is used by solar power plants of this type. We know that solar radiation heats these pipes, which are filled with thermal oil with a temperature of more than 300 degrees Celsius. The hot oil moves through these pipes to the center of the solar power plant, where a proportion of its thermal energy produces steam for a turbine. The rest of the oil energy heats thousands of tons of the substance in these heat storages to a temperature higher than 300 degrees. Then, in the evening or at night, this hot substance produces steam for the turbine, and this is one of the advantages of solar panels, which produce electricity only when it is sunny. In addition, one of my old videos described how that hot substance can produce electricity for several non-sunny days in a row if that substance is concrete, gravel, sand, or other cheap materials. The next advantage of solar panels is the ability to generate electricity during a non-sunny winter as good as during a sunny summer if the heat storage is a large mass of soil or waste, as described in this old video. In addition, my previous video described how similar solar power plants can provide a lot of cheap thermal energy for industrial processes for factories, and my future videos will describe the possibilities of supplying the cheap thermal energy for district heating and greenhouses. The use of thermal oil is not experimental but a well-proven technology, which has been in use for more than 20 years, and investors have already built more than 100 such power plants with a total cost of about $40 billion. Unfortunately, these mirror systems generate expensive thermal energy, about 2 cents per kilowatt-hour, and therefore their electricity is expensive. That is why thermal energy from our mirror dishes should be 4 times cheaper, about half a cent per kilowatt-hour. So, our chip mirror dish should have a similar receiver, which will heat thermal oil to a temperature higher than 300 degrees. These are more decent options for receivers for heating liquids. Now we see that a dish with a receiver should rotate from morning to evening according to the movement of the sun across the sky. This rotation is done by a device called a dual-axis tracker, and this device is widely used as a location for solar panels. Of course, our solar power plant will consist of a large number of mirror dishes which heat hundreds of thousands of tons of chip substance to approximately 300 degrees during solar hours. This thermal energy will generate steam for a turbine both day and night. This is the formula for the cost of thermal energy from our mirror dishes, and here we see that the cost is 2 times worse than the level we need. This is the cost of the trackers which must rotate our mirror dishes from morning to evening, and this cost is consistent with the offers for their sale, but we must add taxes, logistics costs, and installation costs. This is the same formula, but it leads to the heat cost we need, half a cent per kilowatt hour, which allows us to generate electricity at 5 cents per kilowatt hour for victory over thermal and nuclear power plants. Thus, our formula describes the conditions for that victory, and here we see that we must reduce the cost of manufacturing and installing our tracker to the level of $40 per square meter. That is why I plan to experimentally test several ideas for very cheap trackers and will describe my experiments in future videos. In addition, one of my future videos will compare those cheap dishes on dual-axis trackers and these my solar heaters, which do not require any trackers and their chip mirrors are motionless from morning to evening.